everyone. Today I'm going to talk about sets and functions. Finally, we moved on to the next chapter. Specifically today, I'm going to focus on sets, and on next session on Friday, we will talk about functions as well. So what is a set in mathematics? A set is an unordered collection of objects. When we say unordered, not necessarily is unordered. Even if it is ordered, is okay. But what we are saying is that order doesn't matter inside the collection in this set. So a set is an unordered collection of objects called elements or members of the set. Usually we call them elements or members. A set is said to contain its elements. For example, A belongs to capital A. It means that A is a member of this set. And if it's not, we can note it by this one. Okay, so you already know the basic definition of sets, but in pure mathematics, especially when we talk about sets, right away we understand that there is a big problem with this definition because in paradox of Russell, it was shown that the collection of all collections doesn't exist because based on a contradiction, we reach empty set is equivalent to that set, which is a contradiction. And I don't want to go deep into the details related to pure mathematics, but just know that this definition is not as solid as we expect. Even we define a universal set here, which doesn't exist in nature somehow. But when you define it, we can solve many problems, and that's why it gets faulty, because it can relate to the real nature as well. So we will talk about it later. But let's take a look at some examples, like set A. And we show all the members of this set using curly brackets like this. So this set contains 3, 9, 19. And the order doesn't matter. You could even write 19 as the first element. And for example, B, it can contain letters, characters, not necessarily numbers. So any collection of objects that you can imagine, even your names can be inside the set. Or for example, about set of numbers, which we will talk about here, and it could be infinite. Not all the sets are finite. So in that scenario, we can show it by 3 dots that continues until infinity. Or we can even define sets like this. X such that, so whenever you see this straight line, it means that such that. X such that X is an even positive integer number less than 5. And it means that you can write the numbers yourself, right? So instead of just giving you the numbers, we can have this definition. Because sometimes the numbers, the members that you have inside the sets are too big that it's better to write the whole thing in just one sentence. In this scenario, it's not the case, but for example, let's say less than 1 million. So I don't want to write 1 million numbers. Just with this sentence is good enough. So this notation is important. X such that X has this condition. Right. Let's move on to system of numbers, and we can show them by a set of numbers like this. So we can denote it by n, natural numbers. Natural numbers in many books doesn't contain 0. And if you see, for example, in some books, and I also prefer not to consider 0 inside natural numbers. I will show you why. And we can start from 0 or 1 and go to infinity one by one like this, and we call them natural numbers. What about integers? Integers have the same elements, but only the positive ones. You see, I mean, the integers include also negative ones beside the positive ones that you have inside the natural numbers. So we could say natural numbers are a subset of the set of integers. And I will show you the definition of subsets, and we will talk about it later. But for now, remember that N is a subset of Z, Z is a subset of Q, Q is a subset of R, and R is a subset of complex numbers. So when we denote it by a positive sign over integer, it means that this is very similar to natural numbers, right? So again, it's important to consider zero inside it or not, and that's why in some books they have different opinion about it. I usually even don't use such a set. I use either natural or Z. And even we have a W, and for example, some books, they show this one as W to say this one contains, for example, 0. Anyways, let's move on to rational numbers. We can show rational numbers like this. P over Q, such that. So we show that what are the values that P can have, and also for Q. P can get it from Z, Q also from Z, and Q not equal to 0. And for example, why I don't like 0 to be considered in natural numbers, because you can easily show here N without specifying that Q shouldn't be equal to 0. So you can also define Q like that. That P belongs to Z and Q belongs to N. And that's it. You don't need to mention about this. So for real numbers, it includes members from rational numbers and irrational numbers. For complement, I will show you that how we can denote them by using a prime or C over it. But if I want to give you examples, like example 2 is a rational number. 2.12 is a rational number. 2.111 goes to infinity, and we show it like 2.1 and over 1. We just show a line. It means that it goes to infinity by this trend. All of them are rational numbers. But when you have a case, for example, pi number, that decimal points just keep going, or any numbers that you can't see any trend for it, like 3.278, and it continues until infinity. And such numbers are irrational numbers, and they are not inside the set of Q. Okay? Or for example, root of 2. Again, we have the same situation. So together, rational numbers and irrational numbers, they are called real numbers. That we are dealing with them a lot in most of our problems. But also we have complex numbers, which contains also imaginary dimension added to the real number. It means that, for example, 2 itself is a complex number, but 2 plus an imaginary part, for example, I will show you also later, if necessary, that how we can represent complex numbers. Anyway, know that real numbers for the time being is a subset of C, and I will even define for you what is a subset. Okay, and for intervals, we use such notations a lot because they are used in many problems. Like whenever we have closed boundaries like this, it means that X contains A and B as well. But when you show it with parentheses like this, and it means that A and B are not included in X. So when you say X such that X is between A and B, it means that X cannot get its value from A or B. It should be between them. And you can even show boundaries like that. In mathematics, sometimes they call them boundary points, and it has some theorems related to what point exactly we can call boundary points. But when you hear that name, just that's related to it, or lower bound and upper bound, you hear them a lot in the books. So what about equal sets? When two sets are equal to each other. Let's read it together. Two sets are equal if and only if. It means that this is a biconditional case. They have the same elements. Therefore, so their elements should be the same. Therefore, if A and B are sets, so it should be proved that first of all they are sets, not something else. Then A and B are equal if and only if for all x's, x belongs to A and it implies this one, and this one implies this one. This is the biconditional case, so by implication. So you see, the things that we discussed in chapter 1 was necessary for us to understand the terms that we are using in the next chapter. So it was a kind of introduction for you. That's why we don't ask that much questions directly from chapter 1. It was not that much necessary for you guys to know about the proof of theorems. But it's important just to understand them, because now that I use a quantifier, you should know what it means. So in that scenario, we write A is equal to B as two equal sets. Let me show you one example, like these two. These two are exactly equal because order doesn't matter in sets. And I will show you if order matters, we show them by tuples, and later we talk about it. Or even when you have repetition of the same elements like this set is exactly the same as this one and this one, because based on the definition, for example, 1 belongs to A, and at the same time, 1 belongs to this set. So these two sets are equal based on this definition. See? So the frequency of an element doesn't matter. The sets are equal if that's the case. There is an important set which we hear about it a lot and very useful, which is called the empty set. And there is a special set that has no elements inside it. And this set is called empty set. And it is denoted by this notation. And sometimes by this notation. Just two curly brackets, nothing inside it. And it happens often that you mistake these two notations with this one. This one is actually a singleton set. It means that it contains only one element inside it. So if I want to say what is this one, this is an empty set. What is this one? This is a set which contains empty set. Two different things. If there is a technical problem, please let me know again. Otherwise, for questions, let me finish it, and I will answer them all. Okay, so I will talk about this later again, and you will see even the differences better. And we have a diagram named Venn diagram. This one is very useful, especially when you are talking about several sets and you try to understand what are the relationships between them. Usually for showing the elements, when it has so many elements, it's not useful, but usually to show the relation between sets, it could be useful. It can simplify things. And in statistics, we use it a lot. So assume that we have two sets. This one we call universal set. Although I mentioned about the paradox in Russell, we don't care about it in practice. We just assume that we have a set which contains everything. So all our universe is just limited inside this box, which we call the universal set. And we define a set named V, and it contains some elements. So these are the elements. So it has 5 elements inside it. I'll also show you the subset, the Venn diagram related to it, and it will make more sense. So the set A is subset of B if and only if every element of A is also an element of B. And we use this notation for it. So you can also define it like this. For all x's, x belongs to A, so it implies that x also belongs to B. And let me show you in the Venn diagram, like this example. We have a universal set, everything going on inside this universal set. And A is a subset of B. Why is that? Because any element that you can consider here, it is also inside B. Again, any element you can consider inside A for sure is inside U. So any set that you can imagine is a subset of universal set. What about empty set? Empty set is inside all of the sets. It means that it's the subset of all of the sets that you can imagine, even itself. And to understand it better, let me tell about this. So for every set, name it S, every set that you can imagine, we have these two rules. That empty set is the subset of that set, and the set itself is a subset of the set S. It means that if you have a set named S, then it is the subset of itself. So this is clear, I guess. But what about proper subset? In this case, it means that they are not equal, but at the same time you say that set is the subset of the other one. So instead of having this notation, you will have this one. Like the previous example. For example, A, you can say this is a proper subset of B. And that's why instead of saying proper subset, we can just use that notation. But let's take a look at this example. We want to show that two sets are equal. And in that case, if you don't have all the elements, sometimes this is very useful in order to assume that, to show that two sets A and B are equal, we show that A subset of B, at the same time B is a subset of A. This is a good way to show that. But even as an easy example, let me show you what it means. Like, for example, assume that I want to show that these two sets are equal. So you know the elements of this set easily. This one, we should translate it or transform it into the same format. X such that X is a subset of the set. So I should write all the subsets of this set, and all the subsets are the sets themselves anyway. So the subset of this one, empty set, is a subset of all sets. So I should write this. And just a singleton set, like the set of containing only A, it could be this one, and also a singleton B. And each set, as we mentioned, is a subset of itself. So this one I write it too. So you can see these two are exactly the same. If I consider, for example, empty set, is it inside this set? And can I say, for example, A, the whole A set is a subset of B? Yes. Can I say B is a subset of A? Because all elements that I have here is inside this one as well. And yes. So we can prove that A and B are equal. Or directly you can, even if that's easy that you can see all the elements, it's clear that they are equal anyway. So there's a good note here that we should pay attention to. That, for example, in the set A, this element is actually belongs to A. So the set which contains A belongs to A. But A itself doesn't belong to A. We should be very careful about these things from now, because this is a set inside another set. This is just a number, just an element, okay? We should be careful about this notation, because I didn't mention anything about A inside it. I mentioned just about a set containing A. The same story about the empty set that we mentioned. What about size of set? What do we mean by that? It means that the number of elements that you have inside your set. Like, for example, this one. Let A be the set of odd positive integers less than 10. It means that we have 1, 3, 5, 7, 9. 5 number of elements. So in that case, I can show it like this. And for example, for this one, what is the size of empty set? We have 0 because empty set doesn't contain any members inside it. Or English alphabet, it contains 26 letters inside it. So size of a set is easy to understand. And what about power set? Power set is the set containing all possible subsets of that set. So it's better I show it in an example to understand it better, and we denote it by P and inside it S. As an example, let's say what is the power set of the set which contains 0, 1, 2 as its elements. So the power set of this one, Also, I tell you about something that can save your time. Let me show it by using this pen. So whenever we are talking about, for example, the size of the power set, like, for example, the size of our power set, I can calculate it by 2 power the size of that set. Why this is useful for me? Because from the beginning, I understand what is the size of my power set. So when I write the whole set, the elements of that, then I can make sure that I calculate it correctly or not. For example, what's the size of this set? What's the size of it? This is 3. So why? Because it contains 3 elements. So what about this one? What's the size of the power set now? In that scenario, it should be 2 power 3, which is 8. So even without showing that what are the elements of the power set, from the beginning, I should know that it should contain 8 elements. So when I write them, I should make sure that there are 8, otherwise I made a mistake. How to write them? First of all, consider always empty set and set itself inside it. And then try to find different combination, like the singleton of each one of them. So 0, 1, 2. Now I can consider also the pairwise ones, these ones, you see. So I could write all the possible subsets of this set, which we call it a power set. So yeah, now you know exactly what power set means. Now, what's the note here? Note that empty set and the set itself are members of this set of subsets. Yeah, this is the one that we mentioned here. Okay, let me bring back the laser. So what's the power set of the empty set? And what is the power set of the singleton set, which contains only empty set? Take a look at this one. The empty set has exactly one subset, and this is exactly itself. So what's the power set of empty? It is the singleton set which contains empty set. And maybe it's not a bad idea also, I proved that that formula works even here. So what's the size of empty set? No, this is 0. Okay, and if I want to use the same formula, that what's the size of this power set? This is 2 power 0, which is 1. So for sure, I know that the power set should contain 1 element, which is this one. What about the power set of the set, singleton set, which contains empty set? In that case, first of all, I know that empty set is the subset of all sets. It should be always there. And the set itself should be there, because these two are different, as we mentioned. Okay, and again, for the same formula as we used, because this set, what's the size of this set, if you want to say? This is 1, right? The size of it is 1. So what's the size of the power set of this one? This is 2 power 1, which is 2. You see, this formula always works, even for empty sets and singleton sets like this. Now we are ready to get introduced to order and tuple. For tuple, order matters. That's the difference between this one and the sets. The type of set, we could say that here order matters. So when you want to say 2 tuples are exactly the same, like this one, then you should prove that all elements of them at each positions, they are exactly the same. So this is true if and only if AI is equal to BI. It's not AI equal to BJ, because we should show that exactly in the same position they are equal. A1 should be equal to B1. A2 should be equal to B2 until AN equal to BN. That's how we say 2 tuples are exactly equal. pretty much different from the sets, right? Because order didn't matter, and also the frequency didn't matter in sets. Again, coming back to sets, and let's talk about Cartesian product. Let A and B be sets. The Cartesian product of A and B, denoted by A multiplication B, is the set of all ordered pairs. So these ones now ordered, and you show it in tuple instead of showing them in a set. So A and B as a pair, whenever we have only two elements for our tuple, we call them pair. A and B as a pair such that A gets its value from the set A, and you see the conjunction from the logic. We should know about these things from chapter 1. And B belongs to B. So let me show you in an example. Usually, whenever you see the mathematical notations, it may look scary, but as soon as you see an example, you see this is pretty easy. As soon as you understand, it's pretty easy. So what's the Cartesian product of these two sets? In order to come up with the set which contains all the multiplication of them, you can fix the first, for example, element of this set, for example, 1, and consider 1 with all of the members in the other sets. That's the easiest way in order to find out about all the possible elements. So 1A, 1B, 1C, and you write it here. And then fix the second one. And you should move on until the end. And here, fortunately, we had only two elements anyway. And what about the sizes of them? For example, the size of A is equal to 2. Size of B is equal to 3. So if I ask you what's the size of Cartesian product of A and B, what would you say? This is exactly equal to size of A multiply size of B, which is equal to 6. So from the beginning, you should know exactly how many elements this set has. You would understand the size of it. The other thing you should be careful about is that these two sets are not necessarily equal to each other, because the order matters in the Cartesian product. Otherwise, you would multiply this one with this one. Okay, this is totally different. And we should be careful about that. Unless A is equal to empty set or B is equal to empty set. In that scenario, okay, the size of A would be 0, and you see it will make the size of the other one 0, so everything will be empty at the end. Or, for example, A and B are equal, and you have A equal to A, or for example, A equal to any sets, it's clear that the order doesn't matter in the multiplication. A multiply A should be exactly equal to A multiply A. And in the same format, A multiply S should be equal to S multiply A. Why? Because I know that A is equal to S, only in that scenario. If we didn't show that A and B are equal, these two are not necessarily equal to one another. Now let's take a look at this example. We can have Cartesian product for as many sets as we want. And you can see here that you have such a big set now. And if I want to know about the size of them, again, 2 multiply 2 multiply 3. So I will have 12 number of elements inside this set if I want to check from the beginning. So how to calculate it? I fix one element here and one element here. So these are the first two elements inside it. Then I should change the values inside the third one. So these two together, then 0. These two together, then 1. And you may change this one or this one and write the rest of it. For example, again, I fixed for 0 and I consider 2. See? Then I change the values of the third set, and I can construct the whole thing. So you see the Cartesian product works like this, as many sets as we want. For the union of the sets, let me talk about it on Friday, and I will finish the topic related to sets on Friday, and even I will talk about functions. And as you understood, the logic and quantifiers and the things that we mentioned in the first chapter now are very useful in order to have such definitions. Okay, guys, if you have any questions, please let me know. Otherwise, I will see you guys on Friday.